Hi everybody, welcome to chapter 15, where we're going to be discussing some chemical equilibrium. And we actually already started talking about chemical equilibrium a little bit when we discussed the process of a solute and a solvent coming together to create a solution. And we saw that that process works in a forward direction of dissolving and a reverse reaction of crystallization. And that's essentially the idea that we're going to be looking at today and in this chapter is this idea of reactions that can move forward and reverse. So we need to understand, first of all, the definition of equilibrium. And the definition is that it occurs when we have the rate, specifically, of the forward reaction equaling the rate of our reverse reaction. And we call this dynamic equilibrium because neither the forward or the reverse reaction stop occurring. Instead, it's just that both of them are continuing at the same rate. And a common misconception regarding equilibrium is that we have to have the same concentration for our reactants and our products. And when we think of equilibrium, we think of equal, we think of kind of like a scale setup where we would expect to see two pieces at the same level. But that's not the case here because we're not looking at concentrations, we're looking at rate. The rates need to be the same. So I just want to put that out there one more time. Equilibrium does not mean that the reactant and products have the same concentration. Can they have the same concentration? Absolutely. But do they need to have the same concentration? No. So let's look at a quick example of what this could look like. Let's say we're looking at the equilibrium of dinitrogen tetroxide. And so we draw this double-headed arrow to showcase that we have the N2O4 turning into two NO2 molecules, but those two NO2 molecules can combine again to form N2O4. So one more time, this double-headed arrow here shows reversibility. That we can have a forward and a reverse reaction occurring. So let's take a look at what this actually looks like in a graphical portrayal. So here we have our starting concentrations of our reactants. Reactants are going to start at a high concentration, right? Because that's what we're beginning with. Whereas our concentration of our product is essentially 0. So our reaction that's happening here is we have this iron 3+ reacting with the thiocyanate ion in order to make this iron thiocyanate complex. And this is called a complex ion, so it does look a little bit different than something that you are more used to seeing, especially in Chem 1 class, and we'll talk about complex ions in a later chapter. But for right now, you should just kind of get used to this idea that at the very beginning, we know we're going to have a lot of reactant, we know we're going to have 0 product, but as the reaction occurs, obviously our amount of product is going to increase, our amount of reactant is going to decrease. And so you can see that eventually we hit a point where our concentrations stay constant. They are no longer changing, but they are all different from each other. So again, the concentration does not have to be the same as any other substance, but equilibrium hits at this dashed line where the concentrations stay constant for each individual species. So this is just to give you a more visual interpretation of what this means. So how can we talk about equilibrium? We use something called the equilibrium constant expression. And this is specifically for a given reaction at a specific temperature. we always need to specify what that temperature is, because reaction at 25 degrees and even as little as a 26-degree change, so we're changing by just 1 degree, we can expect to see our equilibrium constant change. So how do we write an equilibrium constant expression? Where does this equilibrium constant even come from? Well, let's say we have this generic chemical equation where the lowercase letters represent our coefficients, the uppercase letters represent our compounds or elements. Now, the equilibrium constant is a capital K. So this is easy to get confused with. In our last chapter, we looked at kinetics, and the rate constant was a lowercase k. And equilibrium does deal with rate, right? The definition is that the rates of the forward and reverse reactions are the same. So it makes sense that our value or our variable is k, but this time it's capital. So make sure that you're noting the difference. So we can say that k is equal to, it's always going to be our products over our reactants. And so all this is a ratio. We're just looking at how much product and how much reactant do we have. So as we saw in the graph in the last slide, our ratio, once we've hit equilibrium, is going to stay the same forever because our concentrations stay constant. So that ratio isn't going to change. To be more specific, we can break K down into two different types. We can have something called Kc, where the C stands for concentration. And the way we write that is we take the concentration of the products, so concentration of C times the concentration of D, and we raise those concentrations to their stoichiometric coefficients. So C is going to be raised to little c, and D is going to be raised to little d. Okay, so one more time, we're just taking our coefficients, and our coefficients become our exponents. So those are our products, and then we divide by our reactants. So we're going to have concentration of A raised to little a times B raised to little b. So that is looking at the equilibrium constant when using concentration. The other type that you can do is called Kp, where P stands for pressure. So it's the exact same setup, but instead of using concentrations, we're using pressures. So we can say that Kp is equal to the partial pressure of compound C raised to its coefficient times the partial pressure of compound D raised to its coefficient over the partial pressure of compound A to its coefficient and the partial pressure of B to its coefficient. So one thing that I want to point out here is that this is different from kinetics in that writing our equilibrium constant expression always depends on the stoichiometry of the reaction. We can write K directly from our balanced chemical equation. Whereas in kinetics, we had to look at the mechanism in order to determine the rate law. We couldn't just automatically assume that we could use the stoichiometry. Once we knew the mechanism, we could use the stoichiometry. But here, the mechanism doesn't matter. So no matter what, we can just look at our balanced chemical equation and immediately write our equilibrium constant. So let's look at some examples. I recommend trying these out on your own first. You can go ahead and pause the video, see if you can write out the equilibrium expressions for these two chemical formulas. So for our first one, I'm going to write it up here just so that there's a little bit more room. We can say, again, you can write it as Kc or Kp. The most common method is Kc, so I'm just going to write it using the brackets, the concentration brackets. So K is equal to, we take the products, so it's going to be H2S times H2O, and H2O is going to be squared because its coefficient is 2. That's going to be over the hydrogen, H2, raised to the third. And then SO2 raised to nothing because it is just 1 as its coefficient. So that's our first one. For our second reaction, we can say K is equal to, same idea, start with your products. So chlorine has no exponent. Carbon dioxide is raised to the fourth. Fluorine is raised to the fifth. And then our reactants, so C2F5Cl raised to the second, and oxygen raised to the fourth. So if you had the concentrations, you would just go ahead and directly plug them into this equation and solve for K. Now it's possible that we could be looking at Kc and we want to know the value of Kp or vice versa. And these two numbers are going to be different because a pressure and a concentration are not necessarily the same amount. So we can relate the two of those, Kc and Kp, using a formula. Now remember, Kp is our pressure, Kc is our concentration. And so we're going to assume or use our pressure in atmospheres because we're going to be using the gas constant in our equation. So the equation we're using is Kp equals Kc times RT raised to the delta N. So let's talk about what all of these different pieces are. Kp and Kc, we understand, we looked at those previously. R is our gas constant. And the gas constant is 0.08206. And remember, your units there are liters times atmospheres per mole times Kelvin. T is going to be our temperature, and it has to be in Kelvin. And then delta N is our change in stoichiometric coefficients. And so remember, anytime we're doing a change, we always do our final minus initial. So in this case, it would be our moles of products minus our moles of reactants. And again, we're just looking at the stoichiometric coefficients. We don't need to do any math if we know like the grams or the molarity or anything. We don't have to find our moles. We're just using those coefficients. So let's try out a problem where we utilize this equation. So we have here the formation of ammonia, and we're told the value of Kc, specifically at 400 Kelvin, and we want to know what is Kp at that temperature. So our equation was Kp equals Kc times RT raised to delta N. So Kc we have is 4.5 times 10 to the fourth, right? That was given to us, times R is a constant, and then times T. T was given to us and it's already at Kelvin, so we're good to go there. And then that gets raised to our delta N. So here's a chance for us to look at what that means. On the left side of our equation, we can add up our coefficients. There's technically a 1 in front of the nitrogen and a 3 in front of our hydrogen. So we have a total of 4 as our stoichiometric coefficients on the left side of the equation. Again, all we're doing is taking these coefficients, technically there's a 1 written here, and adding them together. Whereas on the right side, we have only 2, right? That's the only coefficient that we have. So since we take products minus reactants, it's going to be raised to the 2 minus 4, which we know is -2. So remember that you have to use the order of operations here, right? So you're going to do parentheses first, which is multiplying these two numbers together. You're going to start there, multiply those, then you're going to do the exponent. So once you find that product, you're going to raise to the -2, and then you can do your multiplication times the Kc value. And so once you're done with that, try it out for yourself, see if you're getting the same thing, but the Kp value that I got is 41.7. So you can see that our values of Kp and Kc are bound to be vastly different, and that's okay. So let's keep looking at our constant, get a little bit more information about it. What are the units of K? You've noticed I haven't been writing any units. That's because there are no units. And the reason that there are no units is because it's a ratio. So since we have concentration on the top and on the bottom, or we have pressure on the top or the bottom, those cancel out. We end up with a ratio. We don't need any units. We always have to write out the temperature of our reaction because K changes with temperature. We already mentioned that before. Whoa, don't know what happened there. So you can see this example down below where we're looking at the reaction that I had written out at the very start of this lecture with nitrogen dioxide and dinitrogen tetroxide. And so we can take that information and end up with a given ratio at a certain temperature. So normally we have to write out, or you might see in a question, the temperature given to you. That doesn't mean that you necessarily need to use the temperature in the question. It just has to be given to you because K is associated with a given temperature. But depending on the way that we might manipulate our chemical equation, we can change the value of K. So for instance, what happens if we reverse a reaction? So if we started off at the beginning of this lecture with this chemical equation, what if instead of starting with A and B, we're starting with C and D? So if we reverse it, it becomes CC plus DD makes AA and BB. So in this case, our products are now the reactants, and our reactants are now the products. And remember, in order to solve for K, you are taking the products over the reactants. So what we just did here is we swapped what went in each space. What was in the product portion, the numerator, is now in the denominator of our K expression. So in other words, if the first one in blue is our forward reaction, and the one in red is our reverse reaction, we can say that K reverse is equal to 1 over K forward. In other words, it's the reciprocal or the inverse of the opposite direction. So for example, let's just see what this would look like with an actual number. Let's say for a given chemical reaction, we'll say K of the forward reaction is equal to 3.5 times 10 to the second. So what we would do to find K of the reverse is we would take 1 divided by that value, and our K of the reverse would be 0.00286. So one other thing that you'll notice, since we're taking a reciprocal, one of the reactions is going to have a large number, a number greater than 1, which in this case is the forward reaction, and another one is going to have a number less than 1, which in this case is our reverse reaction. So this is why it's very important that you're always writing out the chemical reaction that you're talking about. What were your reactants in the reaction? Because the forward and the reverse reaction eventually are both going to be happening at the same time, but they have different K values. So you always have to specify what your chemical equation is. Now let's look at what happens if we change our stoichiometry of our chemical reaction. Now let's say that you were running a chemical reaction and your reaction was A plus B makes the compound AB, and you found that the value of K for that is equal to 3, hypothetically. Well, maybe we want to use twice as much of each of our reactants. So if we use 2 times as much of A and 2 times as much of B, that means we expect to make twice as much AB, right? Well, what that means for us is we took this first equation and we multiplied it by 2. So you can see up here in the text, it says when the coefficients are multiplied by a factor, in this case that factor is 2, then the equilibrium constant is raised to a power equal to that factor. Because remember, these are ratios and the coefficients become exponents. So since these 2's would become squareds in our reaction, we can say that K then has to be equal to 3 squared. So all we did was take the fact that we multiplied the reaction by 2 and turned it into an exponent for K. So the value of K for this new reaction would be 9. So we looked at reversing reactions, we looked at changing stoichiometry of reactions. So what happens when we have to put multiple steps together in order to get an overall reaction? And we looked at this when we were talking about mechanisms. We've looked at this in thermodynamics. And so I call this the Hess's law of equilibrium. Now, Hess's law is specific to thermodynamics. So this is not actually associated with Hess's law, but the way that we solve for the equilibrium constant is the same as how we solved for the enthalpy in Hess's law. So if we have multiple smaller equations that come together to form an overall equation, how can we find the value of K of the overall equation? So let's say, for instance, we have 2 reactions, 2 steps. So we have A plus B makes AB. And so in our previous slide, we said that K for that reaction was 3, so we'll keep that the same. And then we have a second step to our reaction, right? This is our first reaction, this is our second reaction, which is we have D decomposing into AB plus C. And for that reaction, we have a K equal to 2. For the overall reaction, we would say that the overall is A plus B plus C makes D, and we want to find the value of K for that overall reaction. So we do this the same way we did Hess's law with enthalpies. So here are the generic rules for how to undergo a Hess's law problem. What you want to do, is start off by checking the reactants. And what I mean by that is look at the reactants in our overall equation. So our reactants in the overall equation are A, B, and C. Do we see A, B, and C as reactants in our blue equations? So right now we say, okay, well in reaction 1, A and B are reactants, so that's good. In reaction 2, C is a product, so that is not good. In order for us to take C from a product and turn it into a reactant, we need to reverse that reaction. So we're going to reverse it so that it becomes AB plus C makes D. And so since we changed the reaction, that means that our value of K is going to change. So remember, a few slides back, we said if we are reversing a reaction, K is now equal to the inverse. So 1 over the value of K, which is 2. So our new value of K for this reaction is 1/2. And we can now ignore the blue second equation. So that's your first step. Check the reactants. And then the second part is check the products. So we do the same thing. In our overall reaction, we want D to be the product. And now that we've reversed our second reaction, we do have D as a product. So that's all good. So now our reactants are in the correct spot and our products are in the correct spot. Next, what you would do is check the coefficients. So do the coefficients in our bottom equation match the coefficients in our top equation? So we need 1A. We look up in our blue equations, blue and purple, and we see that we have 1A, so that's good. In our red, we need 1B. We can see that we have 1B in our blue equation. We need 1C. We can see we have 1C in our purple equation, and we need 1D. We have that in our purple equation. So here we don't need to change any coefficients, but if you needed to, you would use the rule from the last slide that we did. If you multiply by a certain number, then you have to multiply or raise your K value to that factor. If you divide by a number, you raise K to the inverse of that factor. So the example that we looked at before was if we multiply our reaction times 2, K gets raised to the second power. If instead we were dividing by 2, K would get raised to the 1/2 power, or the 1/2 power. So our last step then is to cancel out intermediates. And this is just to make sure that you have everything where you need it to be. So remember, an intermediate is something that gets made in one reaction and consumed in another. So our intermediate here is AB. So we can cancel AB out. And then we're left with A, B, C makes D. So then our last step to find K of our overall equation is we take K of the first equation times K of the second equation to get K of our overall. So K1 is 3 times K2 is 1/2. So K of our overall is 1.5. So what you would be given in a question are the two blue equations and the red equation. And you would be asked to solve for K of the red equation the same way that we just did now. So that's what happens if we manipulate any given chemical reaction. But something else that we need to pay attention to is the state of matter of any species that we have in a chemical reaction. Because when we're dealing with equilibrium, we can actually only involve anything that is liquid or aqueous. And so we call this heterogeneous equilibria. Heterogeneous because we're looking at different phases in one chemical reaction. So only gases or aqueous solutions can be used to find K. Only gases or aqueous solutions can be used to find K. The reason that we do not use liquids or solids is because their concentrations never change. And we can prove that by looking at the concentration of water. So water, remember, has a density of 1 gram per milliliter. So if we have 5 grams of water, that means that we also have 5 milliliters, right? 5 grams of water, we also have 5 milliliters of water. So if we wanted to find the concentration of water, we could find molarity, right? Molarity is moles per liter. So we would have to take 5 grams, convert that into moles. So 1 mole of water has a mass of 18 grams. So if we do 5 divided by 18, we get 0.278, and that's our moles. And then we divide by our volume. Remember, our volume needs to be in liters, so 5 milliliters would be 0.005 liters. So 0.278 divided by 0.005 gives us a molarity of 55.6. And if we did the same thing but with 10 grams and 10 milliliters, or if we did it with 50 grams and 50 milliliters, or 1,000 grams, it doesn't matter what you use, it's always going to end up being 55.6 molarity. So I challenge you to try this out, see if you're always getting 55.6, and that will kind of help show, well, a liquid is always going to have the same concentration. So we can't use that because we don't see it fluctuating before it hits equilibrium. So we're only going to use gases or aqueous solutions. So let's say, for example, we're looking at the reaction of the decomposition of calcium carbonate into calcium oxide and carbon dioxide. So calcium carbonate is a solid, calcium oxide is a solid, and carbon dioxide is a gas. So at this point, when we're writing K equals products. So we're going to look at CO2 because we can't include a solid. And then over, well, we can't include a solid, so our equilibrium expression is only equal to the amount of carbon dioxide that we have. So right away, you should just cancel out or cross out any liquids or solids that you see so that you don't accidentally put them in the equilibrium expression. So let's look at a few of those examples and write out our equilibrium expressions. So for our first reaction, we're looking at gaseous oxygen turning into liquid oxygen. And so again, immediately you should point out, oh, we have a liquid as our product. We know we're not going to include that. So we would say K is equal to, we know it's products over reactants. Well, we don't have any products here. So just put 1 as our products over our reactants, which is just the O2. For our second one, we have aqueous, we have gas, and we have liquid. Cancel out that liquid. So K is equal to carbon dioxide over carbonic acid. And those are your values or your expressions for heterogeneous equilibrium. So it's done exactly the same way. The only difference is that now you have to pay attention to the states of matter as well. And you can see for this last example that we did, it's okay that we have aqueous and gas in our equilibrium expression. They don't need to be the same, they just can't be liquid or solid. So one last point that I need to make about K is its magnitude or its value, size. And so we can determine, based on the value of K, if a reaction is product heavy or reactant heavy. And what we mean by that is eventually when we hit equilibrium, are we still going to have more reactants than products, or are we going to have more products than reactants? So if K is greater than 1, that means that we have mostly products. Because remember, our value of K is equal to products over reactants. P for products, R for reactants. So if we have more products, we have a bigger numerator. A bigger numerator means we're going to get a value greater than 1. And since there's products, and when we write out a chemical reaction, it's always reactants on the left, products on the right. So if we have more products, we say the terminology is that the equilibrium lies to the right, because the products are on the right side of a chemical reaction. So again, if you're thinking of like a seesaw or a scale, we have more product concentration-wise, so we're going to see the right side tipping down. If K is less than 1, we're looking at mostly reactants, because again, if we're looking at more reactants than products, that means we have a bigger number in our denominator. So if a bigger number in the denominator than in the numerator, we get a value of K less than 1. And if you ever forget this idea, just plug in random numbers. Let's say you're doing 1 over 100 versus 100 over 1, right? 1 over 100 is going to give you a number less than 1, 0.01. And that's when we have a bigger number as our reactants, whereas 1 over 1 gives you a value of 100, which is greater than 1, and that's when we have a bigger value for our products. So when we're dealing with mostly reactants, since reactants are on the left side of a chemical equation, we say that our equilibrium lies to the left. And we can see what that looks like using these graphs again. So at the start, we have 0 product, all reactant. Eventually, most of our reactants disappear as we convert it into products, but it's possible that our products, as we see in this right graph, don't get past the concentration of the reactants before equilibrium gets reached. And so again, we can see where equilibrium gets reached based on where we see these compounds having a constant concentration. So the remainder of the chapter then is looking at how can we solve for K in a chemical reaction, and then what are some ways that K can be disturbed. And so that's what we're going to look at in our second video.